Hi, Mick McQuaid here with a lecture on dplyr from I think this is chapter 3 of the Wickham 2017 book. And in the upper pane, I have the source code for the slideshow, and in the lower pane, a copy of R. Now you can just follow along with this, with the source code of the slideshow, or you can follow along with the slides themselves. It doesn't really matter. This gives you some clues about things you can do in source code. For example, I can use the pipe character, the vertical bar character, to make a multi-line title for the document. And if you look at the slides, you'll see how that plays out. Okay, I have to say a couple things about chapter 2 first. Some very basic things. So we're going to just review a few of these basics as soon as the tidyverse loads. So X gets seq 1 through 6, makes a sequence. So this makes a vector, and we can find out about that vector. The type of its elements is integer. Its length is 6. It has no attributes. It's just a plain, simple vector. It has a structure, and that structure is integers 1 through 6. It has a class, which again is integer. The class would be different if it were a data frame. It wouldn't. A data frame has different data types in its components, so its class is just data frame. Okay, C means combine or concatenate, and we can see if this vector created manually is the same as the vector that we created automatically. And indeed it is true, all the elements are the same. I can add L at the end of an integer to force it to be an integer instead of a double. And when I do so, I find that they're still equal. Nesting doesn't alter a vector, although nesting alters a list. So this vector is still flat, but if it were a list, it would be nested. I can make Z a logical vector. So the type of Z is logical, and it simply consists of a true or false for each element of X equaling each element of Y. It's not numeric, but I can coerce true to 1 and false to 0. So if I say Z as numeric, I get a vector of 1s because it's all true. They're all, 1 equals 1, 2 equals 2, and so on. Again, the type of Z is logical, but I can coerce it to numeric, in which case it's by default double. I can say that Z is equal to X plus Y, and it will just do pairwise addition of X and Y. So Z now contains 2, 4, 6, 8, 10, and 12. The first 3 elements of Z are 2, 4, and 6. And this gives us the exact same elements. The elements of Z where the index is, where Z itself is greater than 7 are 8, 10, and 12. Options are for this current R session, and you can see, for example, the width of the display is set to 80. That means 80 characters across in the terminal. Okay, now dplyr consists of 6 functions, 5 of which are basic, and the 6th one, group by, is simply applied to those basic ones to change the scope of them. So I already said library tidyverse, so let me say library NYC flights 13. This is a package that loads a database of flights from the year 2013 emanating from New York City Airport. So the airports in question are the Newark, New Jersey Airport, the LaGuardia Airport, and the JFK Airport. I can filter these So filter selects rows. So I'm selecting all the rows here that have a month of January, a day of January, and the origin of the flight was LaGuardia. And I can save that to a variable with this arrow notation. Or I can do both. I can both display it to the screen and save it to a variable. And notice when I display it to the screen that it's a tibble, which is a specialized kind of data frame. So the tibble, when displayed, gives us some information that's not available when we display a data frame. And it also doesn't just go flying by. So there are 230 rows here, but they didn't all just go flying by. Instead, we just see the first 10 rows along with the column names and the data types. And anything that didn't fit on the screen. Since I said columns equals 80, R has taken me at my word and only put enough material on here to fit into an 80 column wide space. Now I can change, since my width is wider, I can do this and I get more. I guess I could have even fit 120. And so we see that there are 230 more rows besides these 10 rows here, and 9 more variables. And the variables, along with their data types, are listed here. So I can do some Boolean operations. So I have, for example, and. So I can choose month is equal to 1 and day is not equal to 1. So that's going to give me January 2nd through the last day of January. Month equals 1 and day equals 1. That's just going to give me the flights on the first day of January. Month equals 1 or day equals 1. And you'll notice down here that there are a lot more rows being displayed because it's all the day equals 1 from the other months. And XOR is the most interesting, perhaps, function because it's a little weird. So this is giving me either month equals 1 or day equals 1, but not both. De Morgan's law can be implemented this way, and it the laws mean that the complement of the intersection is equivalent to the or means the union of the complements, and the complement of the union means the intersection of the complements. So those are laws that you should have gotten in a math or philosophy or probability or logic class or something. And I have some in the slideshow. There are some Venn diagrams of them. They're not in the source code. I mean, the reference to the file is in the source code, but the things themselves are not. Okay, so at the end of every section in this chapter, there are some exercises, and these are the solutions to those exercises. So we get the arrival delay greater than 2 hours. We get the destination is either of the Houston area airports. We get that the carrier is one of the big three, American, Delta, or United. We get that the flights took off during the months of July, August, or September. That this is an interesting one. The departure delay is 0, but the arrival delay is greater than 2 hours. That is tough. They're probably running out of fuel in that basis. So there are only 3 flights that fit that bill. Here are flights that have a departure delay of greater than 60, but the departure delay minus the arrival delay, that is the gain, is greater than 30. Or gain or loss, I guess you could say. The departure time is midnight, or the departure time is less than 6 o'clock in the morning. So those are flights between midnight and 6 o'clock. Between month 7 and 9 is going to give us exactly the same output as this one, month in 7, 8, 9. Is NA dep time means the flight was canceled. There is no departure time because the flight never departed, so the departure time is NA. The arrange function sorts. So it's already sorted. I should mention that data frames differ from databases in that their row order matters and their column order matters. And this one happens to be sorted in year, month, and day order. So we're just replicating that with this function. But I can do it any way I want, so I can arrange it by descending arrival delay. And there are some exercises here. Let's see. This gives us arranged so that departure time for flights that did depart will come before flights that didn't depart. This arranges by the exact opposite, so the flights that didn't depart are listed first. Descending departure delay gives us an amount before it gives us the NAs. And here's just ascending departure delay. So these flights that have negative departure delays left early. So this flight left 43 minutes before it was scheduled to. I hope everybody got on board. This gives us miles per hour. So the distance is in miles and the air time is in minutes. So air time times 60 is hours, so it's miles per hour. Descending distance is going to give us the longest flights first, and distance is going to give us the shortest flights first. Okay, the select selects columns by name. So I can select, for example, the first three columns, just the year, month, and day, and I get one for every flight, but I get, plenty. I could select unique or distinct rather, but I'm not going to do that. The same way, now I mentioned before that the columns are ordered. So year to day, year colon day is the same as year, month, day, because that's the order that they're in. I can select all the columns except year through day. And I can select all the columns whose names start with DEP, and that's departure time and departure delay. And that's not case sensitive, so I can do capital DEP and I get exactly the same result. So I can select all the columns whose names end with time, all the columns whose names contain an underscore, all the columns whose names match repeated characters. So this one is interesting because this is a regular expression, and we're allowed to put in as many regular expressions in matches as we would like. So the parentheses are grouping parentheses, so they group around any individual character followed by a repeat of that character. And in this case, there are four columns that have repeated characters in the name. They all happen to be R's, but these are the four columns that have repeated characters in the name. And this is powerful, not because you can do toy examples like this, but because you can do replacements, you can do searches and replacements where you don't know what it is you're searching for. You just know that it fits a pattern, and you don't know what you're replacing it with. It just fits a pattern. So it can save you an awful lot of typing. If we say select and say a column equals the name of an existing column, that kills off all the unnamed columns. So I only get tail underscore num as a result. But if I use the rename synonym, I get all the columns just with the column, in this case, tail num renamed as tail underscore num. I can rearrange the columns. So airtime is like the 15th column or something. And now I've rearranged it so it's the first column, and the everything function just puts everything else besides airtime after it. So some select exercises. So you may wonder after the that previous one, what happens to columns that are referred to more than once? Well, just the first one matters. I can make a character vector of year, month, and day and select any one of those. It's going to select all three of them. I can select anything that contains the word time, and time is case insensitive, but I can say ignore case equals false, and then I get a result of 0 rows. If I say ignore case equals true, I get the default, which is all the rows. Mutate adds new columns that are functions of existing columns. You're often going to want to do that. So we're going to first create the SML flights. What is that? Small flights? All the columns that end with delay. So now we're going to mutate that. We're going to add a gain column and a speed column to that. The gain column is the arrival delay minus the departure delay. So that's how much time they made up. Usually it's time they made up. It could be time they lost. But usually it's time that they made up. And then the speed, which is in miles per hour. We can also use newly created columns later in the same expression. And when I say later, I mean on a different line. So here we create the hours column and the gain column. And then on the third row, we use gain and hours to make a gain per hour. We might want to keep only the new variables. So if we do that, instead of saying mutate, we say transmute. And then instead of getting all of that stuff, we just get those 3 new columns. There are lots of operators that you can use, and so we're just going to see some examples of those. So column creation example with transmute. So this is going to kill off all the columns that we didn't name. And here we're going to do a ggplot of the diamonds data set. And this one is not going to be that useful. In fact, I made a blunder here. Let me make a correction here. So I'm on Windows, so I have to start an X server here. It would start automatically if I were on Mac, but such are the vagaries of Windows. So I have to go through this dialog every time I want to do this, as far as I know. There might be a faster way to do this. Okay, now this should work now, but it will open behind this window, I think. Let's see. Oh, it opens in front of it. That's good. Okay, but I want it to be over here. I'm going to move it over here. And this I'm going to take out of full screen mode and move it over. Here, because we're going to do some more ggplots. So the first ggplot we're going to do is the very next thing we're going to do. So there's a problem here that all of the cheap diamonds are bunched up down here. So what we're going to do is take the log of the price and the log of the weight, and we're going to do the exact same plot except with those log values. And so that's going to give us a much more spread out version of the most affordable diamonds. So for example, e to the minus 1 is approximately 1/3. So these are probably diamonds that are 1/3 of a carat along here. E to the 0 is 1. So these are 1 carat diamonds right here. So you see that most of the display is taken up by the cheap small diamonds, and very little of the display is taken up by the rarer, expensive diamonds. Offset examples. Okay, so I'm just going to create a vector of 1 to 10 and then show the lag of that vector. And the lag of that vector is going to be 1 less than the vector, so that the first one has nothing behind it. So there's an NA in the first position, and then the others are 1 through 9, where we would have 2 through 10. And lead is just the opposite. We're going to have 2 through 10 in the first 9 places, and then NA in the 10th place. So that's useful in the case of stock market data or any kind of time series data. we can take a cumulative sum, so that's just going to add 1 plus 2 to get the second entry, and then 1 plus 2 plus 3 to get the third entry, and so on. And we can do the cumulative mean also. So these are useful for time series again, and in particular time series that aggregate over time. Okay, ranking needs a lot of explanation, so I urge you to go in the slideshow and click on this link and look at this explanation. We're just going to go through a few simple examples here. So the min rank is the familiar kind of ranking that's usually done in athletic contests, where you might have a tie for second place, and then third place is not awarded. The next one that's given is fourth place. The row number. So notice, why can't I get my cursor back? Oh yeah, I do have my cursor back here. So the row number is just going to skip the NA value. And dense rank is a little bit different. So here we don't skip the third place. So instead of saying first place and then a tie for second place and then fourth place, instead we're saying third place and fourth place. And percent rank is not that interesting to me. I don't really know what you would use percent rank for, but obviously somebody does. Okay, so here are some exercises with mutate. We're going to change the departure time of 2400 to 0. So that's going to be midnight is 0. So that's a little easier to work with, I think. So the largest time is 23:59 now. Then we're going to mutate flights to have a departure minutes. So that's going to be the departure time as hours multiplied by 60, and then the minutes time modulus 100. So that's just going to give us the hours and the minutes and add them together. So it's going to give us the departure time in minutes and the arrival time in minutes. And that's going to enable this arithmetic here, which is arrival minus departure. Now flights 2 is still the same size as the original flights, 330,000 rows by 22 columns. This is dumb. I'm not even going to do this one. This is going to facet wrap. Well, okay, I'll do it, but it's dumb. It's going to facet wrap for every single airport in the United States that these 3 airports serve. Now, there are plenty of small airports that LaGuardia and JFK and Newark don't serve. But look at all these airports. I mean, each one of these plots is incredibly tiny and useless. Much better to look at a subset of these. And here's an attempt to look at all of them on the same plot, which is also useless. Well, it's not totally useless. You'll see a pattern here, but it's mostly a smudge. And notice it takes a long time to render. So there's a dot here for every flight, and some of them are some of them gain and some of them lose. Okay, so here's some more mutate exercises. What is this? Delay rank. This gives us the top 10 most delayed, and this sorts them. So those are the top 10 most delayed. And notice it thinks my display is taller than it is because I set my, let me set my options width equals 60. And then it won't. Well, it still goes off the screen. Okay. Summarize function. Now the summarize function isn't that useful by itself, so we'll see an example of how it's not that useful. If we summarize the average delay of all the flights, we get 12 minutes. So that's, I mean, if you know nothing else about the flight, you know that it's going to be delayed by 12 minutes. But it's much better to know something about it, so we can group them by day. And you're going to see it differs for different days. So we're going to summarize by day. And you see that on January 1st, the average delay was 11.5 minutes. But on January 2nd, the average delay went up to 13.9 minutes. And then it dropped down once we get out of holiday season there on January 8th. It drops way down. So delays are probably bigger on holidays, during holiday seasons than other times. Okay, now the textbook says that it's boring to have a lot of intermediate data sets. So I've got this by dest data set. Then I've got the delay data set. This is all to perform one calculation. And then I've got the delay data set again, still on the one calculation. So according to the textbook, it's more fun to use a pipe character. And what we're going to see here is going to be the same thing, but with no intermediate files. It's all one command. So we say delays gets flights, then group by destination, then summarize, count, dist, delay. So we're creating these columns. Then we're filtering where count is greater than 20 and dest is not Honolulu. And the payoff is we can do a plot like this. So this is actually the nicest plot in the, probably in the whole book, certainly in this chapter. So see, we have a bubble for each airport, and we could label the airports if we really wanted to. You can probably guess that the biggest airports, like the biggest airport on the West Coast is probably LAX or SFO, and this might be Chicago. This might be Atlanta, and so on. I don't know what this is. It's very close, though. It's not very distant at all. And this is the amount of delay. And you'll notice that the amount of delay is greater for airports that are close. And that's because that has an explanation in that pilots tend to be rewarded for not having arrival delays. So they consequently burn more fuel and fly faster, and that has more of an effect when the airport is farther away. Okay, and then there's a little, in the slideshow, there's a little thing about the pipe character. The pipe character is a percent sign followed by a greater than sign followed by a percent sign, which is a very awkward character that's required by R. When Hadley Wickham designed this, he couldn't think of a better way to do this. Since then, base R has come out with the vertical bar followed by the greater than symbol, which I think is a nicer pipe symbol. And we read it as if it were the word then. And it's known as the Magritte Operator. The pipe is also known as the Magritte Operator after René Magritte, the painter. And I have in the slideshow a picture of Magritte's famous painting, This Is Not a Pipe, which shows a picture of a pipe with the words in French below it, This is not a pipe. And it's a statement, it's a very famous statement on representational art or denotative images. Okay, we can say, we can put in an option that removes all the NAs, or we can handle the NAs. So I could just go down here and say options na.rm equals true, and then NAs would always be removed from calculations. But here I'm going to handle it within, instead of saying it as a global option, I'm going to handle it within a series of piped commands. And the result of this is going to be that I've taken all the non-canceled flights and filtered out the canceled flights, I should say. So I have a data frame called not canceled, and then I have that not canceled data set grouped by year, month, and day, and summarizing the mean departure delay for, by day. So I can take I can do something like that. This is similar to that, to make a delays table. So I'm grouping them, in this case, by a tail num. So this is grouping the individual planes and getting the mean arrival delay for those planes. And then I'm going to make a plot of that. So this is the amount of the delay, and this is the number of times the plane has flown, I think. Yeah, the number of flights for the plane and its average delay. So there are a lot of flights that have no delays at all, and then there are a few flights that have an average delay that's huge. So how could you have an average delay of 300 minutes? That's 5 hours. How is that possible? So that's why the textbook says this is misleading and that you have to investigate further. And so we're going to investigate further to find out why that is. We're going to save the delay and n, the number of flights that are made by a particular plane. So this is a plane that had this is a plane that had 400 flights. These two are points are planes that had 400 flights. And this is a plane that had a delay of greater than 5 hours. Now notice that this plane hardly ever flew. It flew maybe one time, ever. And then it was grounded forever. So we see that the variability is great for planes that hardly ever flew, planes that were taken out of service after their first flight. And we're going to see a similar phenomenon in baseball. So you have to have the LAHAM, or whatever it is, batting data frame to do this. You have to have the LAHAM package, which has the batting data frame. And the batting data frame has each point is an individual baseball player. So each one of these points is an individual baseball player, and along the x-axis we have the number of times they were at bat, and along the y-axis we have their batting averages. So 300 batting 300 is a really good deal. If you can find a baseball player who can bat 300, that's pretty good. And so you're going to put them at bat many times. If somebody is terrible at it, you're going to take them out of the batting order after just a few times. So the variability for those who batted a few times is much greater than the variability for those who batted a lot. Okay, now back to the NYC Flights 13 data. Oh, here's the exact same plot. I did this exact same plot with SE equals true, and this just shows that we have very little data for the people who are at bat many times. There just aren't very many of them. So these are standard error bars. The standard error bars are tiny where we have a lot of data, and the standard error bars are huge where we have very little data. Average delay and average positive delay. So the delay can be negative. So when they make up time, they may arrive before they were scheduled to arrive. And that's what we're going to find out here. So we have average delay 1 is the average delay time. The average delay 2 is the average delay only when the delay was positive. Now, variability is a hard concept to grasp. So here we're going to look at the variability of the distance to Western destinations. And you see that the variability interestingly enough, for San Francisco is greater than the variability to Honolulu, which is obviously farther away. Okay, now we're going to explore several different ways to get the first and last flights to leave each day. Now remember, the not canceled data set has midnight as 0. So the first flight on January 1st was at 5:17 a.m., but the first flight on January 2nd was at 42 minutes after midnight. The last flight was at 11:56 and 11:54. Now we can get this same information another way. In fact, we're going to do it, I think, 2 other ways. So this way is going to be the position on a list instead of the actual time. So the first item in the list is 5:17 a.m. The last item on the list is 11:56 p.m. This way puts every flight on a separate line. So range gives us the smallest and largest. So I have to go back here. So departure time and departure yeah, so this is just the first flight and this is the second flight instead of having them both on the same line. Range just gives us the minimum and the maximum. Destinations with the most carriers, you would expect big airports like Chicago or O'Hare or Atlanta to have the most carriers. And we can just count the most flights at destinations like this. And we find that Atlanta has the most. More flights are going to Atlanta than any other, and the second most are going to O'Hare than any other. And we can count one column based on another. So we're counting tail nums based on the distance that they've flown. So this is a weighted sum of the distance that they've flown. We mentioned before that we can use true and false as 1 and 0. So depth time less than 500 means departure time is before 5 a.m. But this statement is true or false. So if we take the sum of this, any time that this was true equals 1, any time it was false equals 0. The sum of this for January 1st is 0. There were no flights. Remember, the first flight on January 1st was 5:17 a.m. On January 2nd, there were 3 flights before 5 a.m. Proportion of flights delayed by more than an hour. So 7% on January 1st were delayed by more than an hour. There's kind of a bulge here at January 1st and 2nd, and then it sort of tapers off after the holiday season ends. I already said that the extra parens cause the results to be displayed as well as stored. So we're starting off with all the flights and grouping them by day. Then we're summarizing those. So now we just have 365 rows in the table. Then we're going to summarize them by month. And now we're just going to have 12 rows in the table. And summarizing them by year, of course, we're just going to have 1 row in the table. If we investigate the not canceled flights, we're going to find that the arrival delays, the average arrival delay is greater later in the day. So this refers to 4 p.m., 3 p.m. Let me see if I can go up here. Yeah, 8 p.m., 7 p.m., 5 p.m. These have the greatest average arrival delay. And I can do the same thing with the variability. The variability is also going to be greater later in the day, although it's a little bit more abstract. So 5 p.m., 6 p.m., 4 p.m., and so on have the greatest variability. The most delayed plane, so notice I've just written the exact same code here, except that I've grouped it by tail num instead of grouping it by the hours of the day. So I did something wrong here. I don't know what I did wrong there. Try it once more. There we go. So those are the most delayed flights. And these are the most variably delayed, most variably delayed planes, not flights. These are airplanes that are most often delayed. And if we investigate this, we'll find that this plane probably only flew once or twice. Okay, so that's the end of this slideshow and the end of chapter 3. And I'll be back with more slideshows for the latest, for the later chapters. But that's all for now. Thanks for watching.